Alright, let's talk about weak bases this time. So the same thing we did for weak acids, we can turn around and do it for weak bases. So let's look at an example. Ammonia is a weak base. If it's put into an aqueous solution, some of the H pluses, some of these waters will split apart, and the H plus will join up with this, and then I'll be left with some OH minus. Yeah, so I get NH4 plus and OH minus, and note the definition. This is acting as a proton acceptor, which is one of the definitions of a base. If I write the equation for KEQ for this, it's products over reactants. Exponents here are 1, 1, 1, 1, because the coefficients are 1, 1, 1, 1. Just like before, this concentration of H2O is, I bring it over, I multiply it here, constant, constant, I put them together, I get a brand new constant we call KB, because I'm dealing with bases. So exactly the same. And we'll do a question down below using it in a second. I just want to point out something else interesting about it. What is the conjugate acid of NH3? Well, in that reaction up above, it's NH4. Yes? NH4 plus is the acid. This is its conjugate base. So let's write an equation of this thing acting like an acid. So here's right here, NH4 plus H2O gives NH3 and H3O plus. So here this thing is acting like an acid. Ka for this reaction right here would be the concentration of NH3 times the concentration of H3O plus. Both exponents are 1 because the coefficients are 1. Does this go down here? No. Don't put water in. NH4 plus. Yes. That's what Ka is. And Kb is this. Now let's take a good look at these things. I got NH3 on the top over here. I got NH3 on the bottom over here. NH4 on the bottom, NH4 on the top, and on the top I got H3O plus and OH minus. And they look similar, kind of like inverses of each other a bit, except for this. So if I multiplied these things together, if I multiply this times this, I would get cancellation, true? That and that would go, and bottom and top would go, and I would be left with only H3O plus and OH minus. And from previous learning, we know that the concentration of H3O plus times the concentration of OH minus is Kw. Surprise. Yes, so this is true then. Kw is Ka times Kb. This tells you that the dissociation constant for any of the conjugate bases can be obtained from the value of Kw divided by the value of Ka. So often when I look in some sort of table of values for a value for Kb, I might not be able to find it. But I could find, what they often do is instead of Kb tables, they only have Ka tables. And they force you to find the proper Ka for the conjugate acid of whatever base you're looking for. Use this formula and solve for Kb. Our book, at the back of our book, has some of both, but in many places it won't. It'll only have Ka values. Now I just want to caution you here, and I bolded this and I underlined it. This only works for conjugate acid-base pairs like we did here, NH3 and NH4 plus. I can't just randomly use the Ka for acetic acid, which is CH3COOH, and get the Kb for H3O. That's ridiculous. They have to be values. These have to be, this for a conjugate acid-base pair, I need the Ka for the acid, I need the Kb for the base, then I can use this formula right here. Don't just randomly try and stick it in and use it. They have to be acid-base pairs. So let's try a question. Give myself some space. Black. So NaCN is going to dissolve in water. Sodium compounds, you might remember from previous courses, are 100% soluble, completely dissolves, sodium salt. So if the concentration of NaCN was 0.1, NaCN is 0.1, then it's going to completely break apart, and I'm going to get 0.1 of this and 0.1 of CN. Now, oddly enough, is this thing by itself an acid or a base? No. However, this thing can act like a base, and when it's in water, it acts like a base. However, the CN ions that are produced can then react with water and set up an equilibrium. So CN plus H2O gives HCN and OH minus. So here is my acid, here is my base, yes, here is my acid, here is my base in terms of conjugate acid-base pairs. So inorganic ions can sometimes turn solutions acidic or basic, and it's because their ions they break apart into can start acting like acids or bases. So let's make our chart. I'll make my lines again. Initial concentration of CN minus is 0.1. Initial water, it's a liquid, don't care about it. I got none of this and none of that to start with. Reaction's going to go this way. I'm going to get plus X and plus X and minus X. Why are they all 1, 1, 1? Because the coefficients are 1, 1, and 1. I'm going to get 0.1 minus X, 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 KB, because I'm dealing with bases here, yes. And just for the record, yes, I need that number. I don't have it. But let's keep going for now. So I would get HCN over OH minus over CN minus. I would get X times X over 0.1 minus X is equal to KB. Now, I feel bad that I don't actually have a value for KB here. Let's say that it's 5 times 10 to the minus 7. Just make up a number. It's irrelevant to this question right now. So 5 times 10 to the minus 7 is equal to x squared over 0.1 minus x. I can swing this over, multiply, everything to one side, quadratic equation, blah, blah, blah. Extra math. Before I do that, I notice, whoa, K, pretty small. So initial concentration over KB is going to be 0.1 over 5 times 10 to the minus 7, and that is for sure is bigger than 1,000. So x is small, and that means that 0.1 minus x is pretty much 0.1. Now I'm going to go back up here and get 5 times 10 to the minus 7 is equal to x squared over 0.1. and therefore 5 times 10 to the minus 8 is equal to x squared. X is equal to the square root of 5 times 10 to the minus 8. Now, the question asks me for what? When I put this question here, did I actually look at what I was doing? So, oh, it just asked for the concentration of OH minus. So, I got that. I have X, and the concentration of OH minus at the end is X. Yes? So, which is equal to the concentration of OH minus. So, I've solved that. So these questions are all the same. They're all chart questions, a few nuances here. Sometimes the little letters down here are different, but it's all the same.